Hi, this is a short lesson on some of the assumptions and theory behind multiple regression models. The good news is that most of the theory carries directly over from simple linear regression material that we talked about in Chapter 2. And so this should be short and familiar, just a few minor differences along the way. So 3 things to discuss. What do the coefficients on a regression model mean? Second, what kind of conditions do you need to check or need to be true before you do inference, confidence intervals, hypothesis testing on a regression model? And third of all, how do you measure how good a regression model is doing? Regarding interpretation of the coefficients, might be interested in predicting what kind of gas mileage a car is going to get. So what kinds of things influence the gas mileage of a car? Certainly its weight and engine size are 2 big things that come to mind. There would be other things as well, like wind resistance and so on. Let's stick with those 2. And so I had an actual sample of 26 cars or so and had SPSS do a regression with engine size and weight as predictors and mileage as a dependent variable, and got the coefficients here as we discussed, and as an algebraic equation it looks like this. So question, what is the meaning, for example, of this negative 0.95? We can say each 1 liter increase in engine size. So how does that change mileage? So we assume that weight is fixed, and then because the coefficient is negative, the mileage is going down. That should make sense. A bigger, more powerful engine will get lower mileage. And the number 0.95 tells me that 1 liter increase in engine size results in about 0.95 miles per gallon decrease in mileage. Is gas mileage more sensitive to changes in weight or in engine size? This is a bigger number than this, but you have to realize that the 2 variables don't operate on at all the same scale. The weight of a car in pounds is 3, 4, 5,000 pounds. Engine size, maybe 4, 5, 6 liter engine. So in order to compare apples with apples, what we can do is standardize the variables. So do or redo the regression with z-scores. What's that mean? Convert everything to z-scores first. So there's a z-score for the mileages, a z-score for the weights, a z-score for the engine size. And then let's do regression of predicting z mileage in terms of z weight and z engine size. And that's quite a bit of computation, but SPSS doesn't care, and you get the so-called standardized coefficients right here. And that's what can be used to compare. I look at it and negative 0.658, negative 0.273. The coefficient on the weight is actually larger now in a standardized sense. So since the standardized coefficient for weight is larger, mileage is more sensitive to the same percent change in weight. In other words, what we're saying is if we increase the weight by 1%, say, and then separately increase the engine size by 1%, the 1% increase in weight is going to cause a bigger change in mileage than in engine size. Let's talk about modeling assumptions. There are several things here, very technical, but they're exactly the same as for the 1 variable case. So what we'll assume is, and again, this is what you need before you start doing confidence intervals, hypothesis tests, etc. We'll assume that the expected value of the mileage is a linear function of the input variables that I have. And before, when we had just one input variable, it was the same thing. We just had these two terms. Now we can have as many predictors as we want. Geometrically, this is saying the means actually do lie on a hyperplane. The actual data points will be scattered near the hyperplane, but on the average, if you average things out, they would lie on a hyperplane. We want the independent variables to not be random, same as before. We want the variances of each of the output variables to be the same numerical value, same as before. We want the observations to be independent. So back to the example of the predicting GPA in terms of SAT scores and so on. I shouldn't be using the same student in multiple semesters. And finally, we want the distribution of the output variable to be normal for all values of the input variable. So I pick SAT math of 570, SAT critical reading of 530. Of all of the students who have both of these SAT scores, their GPAs should be approximately normal. Notice one thing that's not being said, and that is that the X's, the predictors or inputs, don't have to be normal. It's the output that needs to be normal. The input, as long as it satisfies the other conditions, can be however shape it wants to be. Outliers are still a problem, though. And then what are some things that I can say, assuming those conditions hold? So a reminder of the notation, here are the actual outputs. This would be like the actual GPAs. Here are the inputs. So these would be like SAT, math and critical reading scores and high school grades and so on. Here are the actual coefficients of the model in the population. I would like to know these. I can't. That's why I'm doing the regression and doing all of this business to begin with. What I can do is calculate the sample regression line coefficients through this equation, matrix equation we had last time. And then once I know what the B's are, I can use those to generate predicted values of the output. Things that are true: the expected value of the B's calculated this way in the least squares sense is beta. In other words, unbiased. This is an unbiased estimator, just like it was in the one variable case. That's great. If it weren't true, then we probably wouldn't spend much time doing this. Second of all, the least squares estimator is normally distributed. Now remember, before you take the sample, B is, which is dependent on the sample, can be thought of as a random variable. That's why we can talk about its expected value and why we can talk about its distribution. And it turns out that its distribution is normal, which is good because then we use like t-tests and so on to decide how good of an estimator the B's are for the betas. And the third, the so-called Gauss-Markov theorem, mentioned in our book and probably about every book. If I look at all estimators that are unbiased and linear, then the least squares estimator given by this formula is the best one. So something notation to write. Suppose I have another estimator and it's going to work in a linear way, so by matrix multiplication. I'll call that other estimator B star. B is the least squares, and now I have any other k plus 1 vector like this. And if I do this matrix multiplication, here's another predictor. I'll call that Y star. It's a vector and then a hat, just to stack all of this notation together because it's kind of fun to write. So that's one thing, that this is saying that B star is a linear estimator. The second thing the theorem asks before it can be used is that it's unbiased. So we expect that B star is beta. And then the theorem applies, and its conclusion is that the variance of B star is greater than or equal to the variance of B. In other words, or to put it the other way around, the variance of B is less than or equal to the variance of B star, so the least squares estimator B has the most precision, the smallest variance of any estimator of this type. And that's another good thing. So all else being equal, you can get more precise results by using this estimator rather than anything else you could try. And the third thing, measures of model fit. So before we had S squared, which was MSE. Same thing here. SSE is the sum of the squares of the residuals. It's the numerator here. And now downstairs, degrees of freedom, just one thing has changed. When we're doing simple linear regression, K, which is the number of independent variables, was 1. K equals 1 for simple regression. And so before, downstairs, there was an n minus 2. So minor change, but the form is the same. And it still tells the same thing. It's the variance of the deviations. And of course, you want that to be as small as possible. Another thing you could do is compute the R squared. So same formula as before, SSR over SST. And the only new thing to discuss, the new problem, is the following. It turns out that when you're doing multiple linear regression, say I'm trying to predict GPA, and I have SAT math and SAT reading and high school math grades and high school English grades and so on. Then I think of a new variable, maybe number of pairs of shoes owned or person's height or something, and really has nothing to do with the problem at hand. But it turns out that throwing in more independent variables like that almost always increases the R squared. Statisticians have known about that for a long time. It's just the way the math works, and it's undesirable because we work by comparing and seeing which predictor has the largest R squared. But if increasing the number of variables increases R squared, then it would say that I should always just throw everything I can possibly think, all the predictors I can possibly think of at the problem, and that's not good practice. If we rewrite R squared, remember SST equals SSR plus SSE, so just unpacking that, and then writing this as 1 minus something. This tells us that R squared is less than or equal to 1, but more importantly, it gives me a place to start from here. So the adjusted R squared is, instead of taking 1 minus SSE over SST, it's 1 minus MSE over MST. This is after I divide by the degrees of freedom, so it looks like this. The degrees of freedom upstairs is the n minus quantity k plus 1, whereas the degrees of freedom for SST is n minus 1. And if I unpack this compound fraction, I get the numerator n minus 1, the denominator n minus quantity k plus 1, then times SSE divided by SST. And now if I compare these two things for R and for R squared and adjusted R squared, the important thing to notice is that this fraction is greater than 1. This fraction is greater than 1, and so I'm subtracting off a multiple of this fraction, which is greater than 1. In other words, R squared adjusted is going to be less than R squared. And this is what you want to have happen. You want to counterbalance this artificial effect of R squared increasing. So R squared adjusted doesn't increase, or doesn't increase as much as R squared. And so this is what you use. So what do I mean use? I mean you compute like 3 or 4 different predictors using different sets of independent variables, and you compare the adjusted R squareds, which you can get from the output screen right there. This actually is S that we just mentioned at the top of this page. Thanks.